Hi everyone, welcome back. In our last video we started discussing Newton's second law of motion, the fact that an object will accelerate in accordance with the net force acting on it divided by the object's mass. Question is, how can we visually represent the net force on an object? Because a lot of times there will be multiple forces acting on an object. So this is where free body diagrams come in as a tool to help us represent the forces acting on an object and help us to better able to determine the subsequent motion of the object. Now, I do want to mention that this is just one of a number of tools for this, but it is particularly effective in a lot of cases for helping particularly high school students learn about physics and to better understand physics. But keep in mind that it is just a tool, and I have come across a lot of elementary physics students before, particularly ones who are already quite bright, and who find this tool not only to be useful but confusing. And if that's the case, but you're still able to solve physics problems without them, then sure, go ahead and use some other method, just making sure that you're showing all of your work, unless you're specifically instructed to draw a free body diagram. So, some basics about these. When we represent objects in these diagrams, we represent objects by dots. Now, if we're dealing with rotational dynamics, we might represent them by bars or something like that, but so far we're not. We're only talking about translational motion, so we represent objects by dots. So it doesn't matter where the forces are acting, just so long as a force is acting on the object. And from the dot, we draw one arrow for each actual force that's acting on the object. And the arrow needs to be in the same direction that the force is applying. In other words, if the force is applied on the object up and to the left, such that if that was the only force acting on the object would accelerate up and to the left, then the arrow should be such that the tail of the arrow is on the dot, and the arrow points up and to the left. So the arrow always emanates from the dot, and the direction will indicate the direction of the force. The lines should be straight. Curved arrows for free body diagrams are always wrong. And if there are multiple forces that happen to be acting in the same direction, you might want to make your dot large enough so that you'll have room to draw those multiple forces. So let's take a look at a number of examples. How about the free body diagram for an object falling without air resistance? Well, that's easy. An object falling without air resistance feels the force of gravity, which we call weight, W equals mg. And if there's no air resistance, then that's it. This would apply for an object not just falling vertically, but one that is tossed up in the air, one that's tossed sideways, one that's tossed at an angle, as long as air resistance can be neglected. So the only thing acting on the object will be its weight. Now, what about an object that is falling with air resistance? So in this case, we'll still have the weight vector acting on the object, but there's also a drag force acting on the object as well, against the direction of motion. And it's important that the object is falling downward as opposed to being projected through the air or something like that, because the drag force is always against the direction of motion. So in this case, the fact that it's falling straight downward means the drag force points directly upward. Now, I should also note that if the object was thrown at, say, a speed that was very high downward, then it would be possible that the drag force could be larger than the weight vector, in which case the object would be slowing down. Now, let's extend the last example and pretend that we happen to know these forces acting on the object. A 19.6 Newton drag force, the object weighs 19.6 newtons, and we have a drag force of 6.6 newtons. So we write our givens, and we use the fact that Newton's second law tells us the net force is equal to mass times acceleration, and the weight is W equals mg, but in this case we don't need the object's mass because they already told us the weight. It's the weight that goes into Newton's second law. Now, we do need the mass indirectly, though, in order to figure out the object's acceleration. So from the given weight, we got the mass. So Finding the net force is what we need to do for Newton's second law, because after all, Newton's second law says the net force equals mass times acceleration. Well, the net force is equal to, well, we need to pick a direction that we're going to call positive. Since the object is moving down and it's accelerating down, I think it's wise to call down the positive direction. So since down is positive, that means the weight is positive, but the drag force is negative. So we have positive weight minus drag force gives you 19.6 newtons minus 6.6 newtons, so a net force of 13 newtons. Okay, so now we know the net force acting on the object. What's its acceleration going to be? Well, there's where Newton's second law comes in. F equals ma, so a equals F net over m. So 13 newtons divided by 2 kilograms gives an acceleration of 6.5 meters per square second. So, just to summarize the whole process, write the givens, show the equation, plug in the numbers. In fact, in this case, what I would do is I would just say A equals W minus F drag all over M, and then plug in the numbers after finding the mass. But either way, you'll get 6.5 meters per square second. If you did the method of plugging in W minus F drag over M for your F net up here, your next step after solving for the mass would be to say that A equals mg minus F drag equals, just A equals W minus F drag over M, so you just plug in 19.6 newtons minus 6.6 newtons all over 2 kilograms equals 6.5 meters per square second. Okay, how about for an object going at terminal velocity? Terminal velocity is the speed that a falling object will have after it has sped up as much as it can until the air resistance force, the drag force that is, cancels the weight vector. Well, in that case, the object isn't accelerating, so the drag force must have an equal magnitude to the weight force, the gravitational force. So notice the arrows here are equally long. So that's something where if you were to draw such a thing on a test, you would need to make sure that your lengths are at least representative of the problem. So what if we had a bullet with a mass of 0.042 kilograms, that is 42 grams? Well, what would be the magnitude of a drag force on that? Well, there's our free body diagram, but remember that since it's a terminal velocity, that's what the previous example was, that means that the drag force must equal the weight. But the weight is just mg, so you plug in the mass, multiply by 9.8 meters per square second for the acceleration due to gravity, and you get a drag force of 0.41 newtons. How about a diagram of a bullet just after being shot downward at a speed much larger than its terminal velocity? Well, in that case, you're going to have a much larger drag force, because if it's going faster than terminal velocity, that means that it's going to be going faster than the speed at which the drag force equals the weight. So if it's going faster than that, then the drag force will be larger than the weight. So you'd have a diagram like this, where you have a noticeably longer drag force vector than the weight. In this case, the bullet, even though it's being shot downward, will accelerate in the upward direction. In other words, that means it's getting slower in the downward direction. So it would have a positive upward acceleration, or a negative downward acceleration. How about for a rope dragging a yellow-bellied weasel horizontally across the floor at constant velocity? Well, if let's pretend the weasel is going toward the right, then we have a normal force up, and again I often label the normal force just lowercase n instead of F sub n. And the tension force is going toward the right, and the kinetic friction force is going toward the left. And again, this is kind of an older diagram, but usually I will label kinetic friction force as a lowercase f with a subscript of k instead of capital F. But in any case, notice that the horizontal arrows have equal length and the vertical arrows have equal length. Why do they have equal length? Because it says it's going at constant velocity, meaning that it's not accelerating, meaning that there is no net force. So the forces that are present must all cancel. So what if that rope is cut? Well, in that case, we get rid of the tension force, and we just redraw the diagram. Copy and paste makes these really nice for PowerPoints. So, if the rope's cut, tension is gone, but all the other forces are still present. Friction is present because it's moving across a surface. So, there will be that kinetic friction force until it comes to a stop. How about a situation where a spring is hanging from a ceiling? In that case, a person takes a ball and uses it to compress a spring upward, suppose. So what would be the free body diagram in this case? Well, we would clearly have an applied force upward. That's what's being used to compress the spring. And that applied force will be canceled by the weight, or actually it will cancel the weight and the spring force. So notice that since it's being compressed in a upward in a vertical spring, that means the spring force is downward. So if this is compressed, and supposedly, since it's not accelerating, because they tell us it's at rest, which is not just not accelerating, but also not accelerating and has zero velocity, that means the net force must be zero. So the length of my applied force vector must be the sum of the length of the weight plus the spring force in order to get this completely right. So we have multiple forces acting on the ball and two downward forces. Notice that I made my dot a little bit bigger so that I had room to draw both of them. So, yeah, you need greater applied force than just the weight if you're also compressing it in a spring. If there was no spring and you had this applied force with this weight, the result would be that it would accelerate upward. So in other words, if you want to not just lift something but accelerate it upward, you need to apply a force larger than the object's weight. But in this case, we're doing that because we need to counteract both the weight and the spring force. So again, it's at equilibrium, meaning because they tell us that it's at rest, and equilibrium means that it's not accelerating at the very least. It often also means that it's at rest, but at least it's not accelerating. So our forces all cancel. How about the same situation, but the ball is released? Well, when the ball is released, that means that the applied force is no longer acting on it. So again, copy and paste is great. So since there's no longer any applied force, we just have the weight downward plus the spring force downward. In fact, when this thing is released, its initial acceleration will be larger than the acceleration due to gravity. It's going to accelerate at a quicker rate than 9.8 meters per square second. So its velocity is going to increase more quickly than something that is simply dropped. So continuing that last problem, what if we're dealing with the object at the instant that the ball has its maximum speed on the way down? So here's where we want to go back to the problem, and it says, suppose the ball is attached to the spring. If it's attached to the spring, that means that it's not going to be leaving the spring. It's going to pull the spring downward with it. So what will happen at the maximum speed? The maximum speed will be such that it's just before the spring will start to be pulling upward on the ball with a larger force than the ball's weight. So here we have weight downward and spring force upward just being equal. Just before this happened, the spring force was less because the spring wasn't extended as much, and it was still speeding up. Just after this, the spring will have extended even more, and the spring force will be larger than the weight, and it will be slowing down. Or at least, yeah, it'll be slowing down, and thus, in this case, accelerating in the upward direction. So at this point, the acceleration, if we're calling down positive, the acceleration is changing from positive to negative at this particular instant, where it's attached to the spring and at its maximum speed. How about the same situation that we just had, but when the ball is at the very bottom of its motion? Well, the weight is still acting on the ball, but at the very bottom of its motion, it kept going past that point where it was at its maximum speed because it had momentum with it, so it's extending the spring even more until eventually the spring force combined with the previous acceleration in the upward direction is large enough that it stops the motion of the ball. But at the moment that it stops, the spring force is still larger than the weight, so there's going to be an upward acceleration at this pausing point. If we were to continue the motion, then the ball would end up moving upward as well, and you would be dealing with oscillatory motion. So here we've had a number of examples where Newton's second law is being used and considered with free body diagrams, and a few situations where we even did calculations with this. So next, let's turn our attention to a problem that you've probably experienced before. If you've ever ridden in an elevator, you've noticed that you feel heavier at the beginning of the way up and lighter at the end of the way up, and vice versa on the way down. At the beginning you feel lighter, and at the end of the way down you feel heavier. Why is that? The reason is because your apparent weight is changing. So let's consider a 72 kilogram man standing in a scale. Calculate the scale's reading when the elevator is accelerating in the upward direction at 2.5 meters per square second. B, when the elevator is moving at a constant speed of 8.25 meters per second in the upward direction. And C, when the elevator is accelerating in the downward direction at 1.5 meters per square second. So, first, keep in mind, what does a scale measure? Do scales measure weight? No. Scales measure normal force. So in part A, where the elevator is accelerating up at 2.5 meters per square second, the question is, what is the normal force? That will give us the scale's reading. Now, when we say the elevator is accelerating up at 2.5 meters per square second, that could mean that it's getting faster in the upward direction, but it could also mean that it's getting slower in the downward direction. Either of those would be an upward acceleration. So, start with Newton's second law, showing our work. Net force equals ma, or sum over F equals ma, if you like this capital Greek letter sigma, the summation notation. Sum of F equals ma. And here we're going to consider up to be the positive direction. Well, what is the net force? Well, if up is positive, we have a normal force upward, and we have weight downward. So since the weight's downward and we're calling up positive, we put a minus sign in front of the weight. And that's equal to mass times acceleration. The question, though, remember, is what was normal force? So add W equals mg to both sides. Substitute mg for W. And just to save ourselves a mathematical step, I factored out the m so that I won't have to plug in as many numbers. The fewer numbers I plug into my calculator, the fewer silly calculator mistakes I'm likely to make. So, we factored out our m, and now we plugged in the acceleration due to gravity, and multiplied by the mass, and we get the scale's rating of 885.6 newtons, rounding to about 886 newtons. Now, what about the constant velocity situation, part B, constant speed of 8.25 meters per second? Well, do you see a v anywhere in Newton's second law? You don't. So the velocity is irrelevant. The acceleration is what's relevant. It says constant velocity, well, constant speed, but we know elevators go in straight lines. So the acceleration is 0. So net force equals 0. Does that mean the normal force is 0? I hope not, because when you're sitting in your chair, that's constant velocity. So I hope the normal force from the chair isn't 0. Otherwise you'd be falling. So the total force is 0. But the total force is n minus w, or n equals w. But w equals mg, so plug in, and in this case you get the scale's rating of 706 newtons. That's your normal weight. When elevators are going at constant velocity, you feel normal. What about the other situation? In this case, just going through it really fast, we have the acceleration downward of 1.5 meters per square second. But remember, I called up the positive direction, so that means if the acceleration is downward, that means the net force has to be downward. Notice how I drew the normal force as being less than the weight in the free body diagram, because I know that the net force must be downward if the acceleration is downward. So we do the same thing as before. I still considered up to be positive, but if up is positive and the acceleration is down, that means I plug in a negative 1.5 meters per square second for my acceleration. The reason I just went through these steps really fast this time is because the derivation is exactly the same as in part A. It's just that the answer is different because we plugged in different numbers. So that's how elevator problems go. Elevator problems are rather common problems in elementary physics classes. So in the next video, we're going to turn our attention to combining Newton's second law with kinematics equations. So hope to see you then. Thank you for watching.